when we're dealing with triple integrals, it can sometimes be easier to do a transformation of coordinates, similar to the way that we did it in double integrals by converting to polar coordinates. So if you go all the way back to our discussion with cylindrical coordinates earlier, we saw that we could take an XYZ location and instead represent it with three different parameters, well, two different parameters, r, theta, and z, where r and theta are really just your polar coordinates for x and y, and the z doesn't change. So just as a refresher, r squared is equal to x squared plus y squared. X and y are r cosine theta and r sine theta respectively. Z doesn't change. Tangent of theta is y over x. So if we have some sort of theta that rotates from the positive x-axis towards the positive y-axis, so it goes in that counterclockwise rotation, and r is the distance from the projection. So if we took that vector and we projected it onto the xy plane, r is that projection vector, and then z is just the vertical distance directly up to it. And that's remember, that's how we do cylindrical coordinates. But what we can do is we can take the volume of some sort of solid and we can break it into cylindrical coordinate regions. We can take it and kind of do this wedge of cheese looking thing that I have here. So this block has some distance or some length, delta r, and it has some arc that's subtended by delta theta. And so but you have a little bit of an interesting case where it's still a function of how far out you are from the origin, and that has to do with the idea like of a circle. And remember that the arc length of a circle is the radius times the angle that's being subtended. So you have it being a function of r based on how far along it is. That's why this piece would be smaller and this piece would be smaller. Even though it's the same delta theta, it might be the same delta r. So you have the same idea of that polar coordinate here, but now we have a height. We have a height of delta z. So you have some sort of solid chunk, and if we take some sort of solid and break it up into a bunch of solid chunks that cover it, then we can approximate the volume of that solid by just saying, each of those chunks, which is delta z times that the flat area. So we take each of those incremental volumes, and we say that the volume is roughly the sum of those incremental volumes, which after we rearrange this quantity is r times delta z, delta r, delta theta. And then we say that the actual volume, instead of being approximated, is the same thing as the triple integral over this region. We call that Q. So we used R when we talked about planar regions, and we use Q when we're talking about solid regions, dV. But we can also use an iterated integral, assuming a few things are valid, right? We typically had to assume some sort of continuity, but in the case of volume, we really don't have to assume that. But we need to know something very particular, which is that if we can describe the region as theta having constant bounds, so that would be theta simple, and then we could say r is a function of theta alone, so you can describe, so if you could describe the projected region in terms of just some starting angle and ending angle, and then r is a function of that angle. And then finally, you have z here. Now notice I did something here. I said z was a function of x and y. And the reason why that's common is because typically we'll be given a function in terms of x and y because that's what we're used to. We're not necessarily used to it being in terms of r and theta. So if we have the xy function, what we can do is we can use the xy function as bounds here. But instead of x, we put r cosine theta. Instead of y, we put r sine theta. So we substitute in these as the variables in those equations. And we say if z goes from here to here, r goes from here to here, and theta goes from here to here, we can have these iterated integrals are dz dr d theta. So again, this is like double integrals where we had r dr d theta, but now we have a triple integral with a dz, and we're going to do some examples with some explicit functions to try to give you a better feel for how to use cylindrical coordinates with explicit functions and how to integrate them.